Okay, so welcome back for this second session of the day about SAR tomography. I remind you, tomorrow you will have a lecture on SAR polarimetry, Wednesday SAR, and Thursday on the advanced applications. Later this afternoon we will have a practical session in the PC room, which is just opposite side. When you get out from this hall, you just cross, and on the right hand side you have a PC room. You will see some of you. If some of you can use their PC, their laptop, it will be much more convenient. Okay, for the others, we can try to open sessions. As I mentioned this morning, there was a misunderstanding with the events department at SUPAERO, and we don't have specific logins for students, but I can open sessions on my name, and you can use the sessions on the computer if you don't have a laptop. Okay, now back to the science and to the technology with SAR tomography. So this morning you had a very nice lecture by Stefano on how he started from scratch, basically explaining the principle of SAR, that SAR can measure distance. It's a fantastic tool for measuring a distance with a very high accuracy. And there are some applications he did not mention, but I don't know if you're aware of this capability of SAR, can measure displacement of buildings, subsidence motion with a precision of a few millimeters per year. It can also measure some displacement, some vehicles that move from space. You can monitor the velocity of ground vehicles with a very high accuracy too. So the main ability of SAR is to detect objects and to localize them very accurately. And this afternoon we are going to investigate how to process the data. Once you have SAR data, how can you transform this data into tomograms? Not the way Stefano presented this morning, which is very complex when you need to interpolate, to make some sums and to go to one space, the other. And there are some specific configurations, which are finally the ones we are looking for when we plan a spaceborne mission, for which the processing is very simple. You will see at the end, it's just a filter. For those of you who studied electrical engineering, a filter is a filter. For the others, it's like a weighted sum of coefficients, okay? And if you choose the right coefficients, then you will build very easily the tomograms. By the way, this is what you will do in the practical session this afternoon, okay? In the practical session, you will load the data, compute covariance matrices. We will see what this means. And from the covariance matrices, you will display tomograms along a specific profile that you choose on the data. So if you can do this, then you are autonomous. It means that if you download the TomoSense data Stefano mentioned this morning, then you apply the same formula, same equations, and you will get a nice result. So this is the objective of the lecture. Okay, so okay, this is the content. So we will start from 3D synthetic aperture radar imaging to the beamformer. Beamformer is a technique to compute tomograms from SAR images, and it comes from a long time ago from antenna array processing, which is in fact the main technique that we use to build tomogram is array synthesis, and whose basics go back to the 80s. All the techniques we are going to present were found by colleagues now 40 years ago. But they were not using it for imaging. They were using it for localizing objects, like localizing a telephone accurately, or estimating in astrophysics the position of a star, or other applications. Okay, so if we go back to the physics of radar, you know that radar, synthetic aperture radar, is based on radar which is operated along a trajectory. Along this trajectory, the radar periodically emits and receives waveforms. And by coherently combining waveforms and focusing them in distance in azimuth, you can get, in case of a nice response, you will get a point-like scatterer. You will get a nicely focused SAR response, which has the shape of a double sync, okay, cardinal sign, in both range and azimuth position. So if you see a response like this, it is very likely that at the exact position of the summit this bell-shaped response, you will have a scatterer. So the expression here of this response is made of several parts. You have, of course, AC, which is the amplitude of the response. The larger the amplitude, the larger the reflectivity of the object. You have this response here in range, which has the shape of a sink, okay, which tells you at which range position, at which distance from the track your target is located. You have an equivalent one in the azimuth direction, and you have a phase term, and this is this phase term we are going to use to estimate the true position of the target in 3D. Okay, but when you do a 2D, a single acquisition, then you get a 2D image. Okay, you might think that this representation is redundant because we can guess R0, the position in range, from this shape, this amplitude waveform here, and from the phase. The thing is that this is always like this in radar, but this measurement here is very robust, but it's not very accurate because you measure the position with a resolution which is given by the bandwidth of the system. So it's 1 meter, 2 meters. Okay. Here you are measuring the position with a much higher accuracy because you are comparing the distance, okay, to the wavelength of the signal. And when you work at X band, the wavelength is 3 centimeters. If you work at L band, the wavelength is 30 centimeters. But here you are comparing the position of the object with respect to the resolution. If you have a very good SAR system, the range resolution is 1 meter. Okay, so you see the order of magnitude is not at all the same. Nevertheless, if you this 2D SAR image results from a coherent integration of the reflectivity of the environment, which is represented here, okay, which is of course convolved or multiplied by the impulse response of the system, the sink, okay, and a phase term which depends on the distance between the sensor and the object. Okay, if we hope we have a narrow enough impulse response, we can simplify this expression to this one, where in fact the 2D SAR image is just a sum within a resolution cell, which is represented here, of the reflectivity of the scene here times an exponential with the phase, and the value of the phase depend on the actual position of the scatterers you are considering inside the resolution cell and on the wavelengths. So 3D imaging, as this was explained by Stefano this morning, consists in combining acquisitions performed at different positions in elevation, for instance, and combining them so that you can create a 3D reflectivity cube, okay, in X, Y, and Z by simply, okay, coherently processing or doing this coherently combining 2D acquisitions performed from these different elevations, okay? And the key point is that you need to sum the values for each resolution cell within each image multiplied by a phase term. You need to compensate the phase term in order to have a coherent sum and to further discriminate this blue resolution cell, which correspond in fact to a 2D SAR resolution cell, which is this one here. And if you perform this processing, then inside the resolution cell, you will be able to further discriminate the red blobs here, which correspond to tomographic resolution cells. Okay, so this is the objective of tomographic focusing. As said Stefano this morning, even if we represent tomograms in the elevation direction, because we like this, we like to look at the object in the horizontal and vertical direction. You don't work in elevation, you just work in the direction which is orthogonal to the radar line of sight. This is the radar line of sight. Okay, so you work in this direction, and after we convert positions to the equivalent ones in elevation. So the processing is very simple. The one that Stefano showed you is called the back projection, which is a very well-known algorithm to do 3D imaging. You just need to take every single 2D image, you interpolate it at the right distance, and you compensate the first term, and you make a sum. But it is easy to do, but when you do this, you still need to interpolate the data. Interpolating the data means that you lose time and you need to choose the right way to interpolate. It's not direct, okay? We can show that in some cases, it is not necessary to actually perform this interpolation. Let me explain you how. Here is a representation of 2D focusing positions sampled along two radar line of sight. Let's say that I have a sensor located here in S1 and another one located here in SM, okay? And they all measure a distance between the scene they are looking at and the sensor. So 1 point, when you measure distance, the point can be located anywhere on this circle here. It is at a given distance. So how do we process this data so that they can be combined easily? We just, in fact, synchronize the data together. So we just project them onto a common plane at a arbitrarily chosen height. Of course, the height we choose to co-register the images should be chosen so that it corresponds approximately to the same elevation. Okay, it doesn't have to be exactly to follow the topography, just some meters above, or maybe 10 or 100 meters, but not 1 kilometer above. Okay, why? Because you know that when you focus, okay, your data are located on a cylinder which surrounds the trajectory of the plane. So you're on a circle, okay? And if you are on a circle and you want all the data to look at the same point, you know that at one moment there will be a divergence of the circle, okay? The pixels which are exactly co-registered at this height will not be co-registered, you know, this pixel here. We look at a very different place compared to this one, okay? So you need to in fact, to co-register the circle so that they look exactly at the same 3D position for a given height, which is called the height of reference. Once this is done, you've done the most complicated part of the work because you have co-registered images. So along this, at this elevation, you can consider that the distance between one sensor and the scene can be decomposed into two terms, okay? One, which is this reference distance that people do for you when you get data from DLR, from ONERA, from other agencies. They have already done this work. And what they give you the KZ parameter, which is the remaining part of the distance. It's a linear approximation of the remaining part of the distance, okay? So the data are co-registered and you get, so this has been removed, okay? And you get this KZ term. Of course, this kind of processing is valid only if you try to focus data in at elevations that are close enough to the reference ones you chose. Okay, but luckily for intermediate resolution data, such as data set with a resolution here in range of 1 meter, this region here covers tens of meters in elevation for airborne data sets. Okay. So this is just a question of geometry. Eh? You synchronize the circles so that they look exactly at the same point on a given plane. And around this position, you can decompose the distance into a linear form. And once you have done this, you can obtain a 3D cube, okay, around this mean position by simply combining this already interpolated data and combine them with the phase term. And so this is what we are going to do today. You just take the data, you take the phase term, and you combine them with the correct weights. So how do we do this in practice? You get a stack of data. So today you will work with a stack of, I think, 6 images, okay, that have been acquired. The image you will work on have been acquired in Africa, in Gabon, by the GLR SAR sensor, and SAR sensor, sorry, and they have been already co-registered at a given height. Okay, so you don't need to do any interpolation. You just need to take one pixel and combine the values of this pixel with the correct weight, which compensate for the interferometric term. Okay, and when you select the right for a given Z value, then you can estimate the reflectivity around this elevation. So this is a coherent combination. For those of you who like signal processing, this can be written with vectors, okay, and with a scalar product of Hermitian scalar product of two vectors, okay? And this vector here is called a steering vector. Why steering? You know, steering is like when you see steering wheel, when you drive a car. It's because when you change the Z value in this parameter, it's like if you were saying the radar, or look in this at this height, or look at this one, this one, this one, then you can estimate the reflectivity for different Z values, okay? So this is what you will program this afternoon. Only this. So how do we, why do we do this? You don't need to believe me when I say, oh, you just need to combine to put phase and you will get the reflectivity. We're just going to show it. So how does, let's go back to classical interferometry. Interferometry, you measure 1 point, okay, at a given distance from the first sensor, R1, for instance, okay, and you don't know where it is located. In order to guess the location in elevation of this point, you need to perform a second acquisition and look for the intersection of the two circles. Okay, so this is what this is the philosophical explanation of what you're doing. In practice, what you do, you take one SAR image, second SAR image, you co-register the SAR image, you make an interferogram, and for this interferogram, you know that the phase is dependent on the height, and from this phase, you can guess the height. Okay, it is not as simple as this because you see that this is different from this. Why? Because when you measure a phase, okay, you can only measure a phase between -pi and +pi, okay, and the actual height you are measuring can correspond to several times 2pi. In addition, so you don't know when you measure a phase, it is always a modulo 2pi, and you don't know this the number of times phase have been rotating around the complex plane. Okay. And this is called phase unwrapping. We're not going to say this in detail, okay? It's just to let you know that interferometry is powerful, it's simple, but there is this phase unwrapping phase that we don't have to do in SAR tomography, luckily. And okay, when I started my PhD, this was the big boom of phase unwrapping. When you were attending conferences, people were fighting. There were I don't know how many papers every year on this subject, and today nobody publishes anymore. There is one solution which is accepted by everybody. Okay, this is now a major subject. Okay, you can download, by the way, this solution on the web for free and use it if you need it. The typical in-SAR processing chain is the following. You take two SAR images, you co-register them, you make an interferogram. This one is very nice, but it is very complex. You know, these are very fast phase variations because there is still the phase related to the position on the reference plane on this one. You can remove this distance from the phase. Once you remove the distance of the phase, the one which remains depends only on the elevation. You unwrap the phase, convert it to height, and you have a geocoded product at the end. And this is mounted now, observed by the CERSI XR mission Francesco mentioned this morning. So it was in 94, I think. So how do you do this? We can, I will, it took some time to build some titles for the presentation. I'd like you to see them. Estimation of a single scatterers with two images. How do you do? With interferometry, it's very easy. You have one image, the other. You say you want to measure delta phi, which is a function of the height. Okay. So what you do, you just take one image, you multiply by the complex conjugate of the other, and you take the phase of the result, the argument of the result. Okay. And the argument is exactly delta phi, if you have no noise, of course. And if you want to measure the intensity, then you just take the two images you have you are working on, and you just take the sum, the mean of the square moduli of the amplitudes, okay, and you get an estimate of intensity. If you want to do it the complex way, okay, you can do it. You can change the way of computing this phase. You can just say, oh, let's say that in fact I did not measure two images, but I measured a vector y, okay, and I can play with two. I can combine these two images with weights, okay, and one of them being a complex with the first phase term. And if you apply the linear filter expression I mentioned before, you get at the end this result, okay, which is complex, okay. And if you display the modulus of the output of this filter, you will get exactly the blue curve here. Okay. And why? Because if you are, I don't know if you are familiar, or if you remember what you studied at school with the complex numbers, okay, but this is exactly the formula of a cosine. Okay, so it's a cosine of this term here. So it means that when phi corresponds exactly to the interferometric phase you want to measure, the modulus here will be maximum. Okay, it will be exactly maximum. It means that this phase will compensate exactly the interferometric phase. So it's another way to estimate the phase. I don't say it is more simple, it's just another way. Here, you just measure a phase, and here you convert a phase into amplitude, okay? And by measuring the maximum of the amplitude, you can guess the phase. Okay, so when you have only two images, there is no advantage in doing this. Okay, except that no, there is no advantage. Okay, measuring directly the phase is enough. But what happens when you have not two images, but you have 6 images, and you have, let's say, three targets? You are looking at more than one target, and you have 6 images, so you have a lot of measurements, okay, lots of unknowns, and you have a large system of equations to solve in order to guess the elevation of each individual scatterer. Okay, this is very complex. Okay? And you need to think, in addition, that the phase may be wrapped, so you need to take into account the wrapping when you solve the system. So it's you can get crazy if you try to do this. And a nice way to do it is just to apply exactly the same formula than the one we did before. We just build a vector with some phase terms, okay? And we try and we combine the elements we measured with the phase term for different Z values, for different elevation values. And when you have a correct Z value, then you will have a big peak, okay? So here, one peak means that you are exactly at the position of a target. So in fact, you convert phase to amplitude, and this is very convenient when you have more than 3 images, okay, more than 2 images, and when you have several scatterers. Otherwise, if you try to do it with the equation, then you will create errors. And I haven't spoken yet of the noise. Of course, all the measurements we do are noisy, so the solution here is extremely impossible to find. Okay, so everybody does this kind of processing, which in fact it's called a matched filter, for those who like signal processing. And I don't know, do you know how I can remove this? No. Oh. Okay, I will play. Sorry? Alt? No. And here? Here? No, my poor title. Okay, no problems. No. Masqué. Merci. Oh, merci beaucoup. Thank you. Thank you so much. You saved my presentation, or at least on this aspect. So when you look at this way of combining the different images, this is, for those of you who remember, this is the exact expression of the discrete Fourier transform. So what we are doing, we're just applying a Fourier transform to the data. Okay, nothing more. Okay. And this is the same comment that Stefano did this morning, saying that when you do a measurement and you want to go to the focused result, you just need to apply a Fourier transform. So then tomographic focusing is just a spectral estimation problem. You receive the data in one domain, okay, in the domain which is represented by the images, and you want to go into the focus domain by applying a Fourier transform in elevation, okay, along the different images. So how can we characterize this this Fourier transform. Here in the preceding slide, I gave you the results of the same processing applied in different conditions. Okay, here you see that we have it's obvious that we have looking at 4 scatterers. Here also, here it starts to be difficult to discriminate the 4 scatterers, and here we have a very wrong interpretation of what's going on. What changed between this and this? We had a different resolution of analysis. The resolution changed. Okay, the resolution is our ability to discriminate 2 scatterers that are closely spaced. Okay, and in this case, it was clearly insufficient. How do we compute this resolution? If we start from the model of the interferometric phase, which is linearized and which correspond to the actual height via this KZ coefficient, and the KZ depend on the baseline, okay? We can put ourselves into a very simple configuration where the spacing is regular, okay? This happens for the story, this happens only with the German pilots, okay? This is a joke, but it is almost true. When you look at the data acquired by the pilots of DLR, you know, the baseline spacing is so precise that you are almost in this condition. It's good, very good, but on the other side, it's not as good because you have high side lobes, okay, and you need to apply some signal processing tricks. But going back to our story, when you have a regular spacing, means you have a space line of between the first image and 2 meters, and the second image you have 20 meters, then again 20 meters, 20 meters. So at the end you have 60 meters of excursion in elevation. Then the model of the phase, the interferometric phase of the scatterer follows this expression, which is it has a geometric progression. Okay, here you see that you have a phase equal to 0, then you have a phase given by d kz z and 2d kz z and until the last term, which is also a multiple of this d kz. So this d kz is called the spectral sampling. So you are looking in the spectral domain at different positions. And when you sum up all this spacing, you get the spectral bandwidth. Okay, so you are exploring a given bandwidth with a different, some small steps inside the spectral domain. When we compute the response, which corresponds to this particular here geometric shape, okay, you get something which is I don't want to do the calculation. It's just you just need to compute some, this is a sum, and we get this strange expression, which is made of 2 parts. In the numerator, you have a sign, and denominator, you have a sign. But here in the argument of a sign, you have something which is big, which is m times this, and this one here, you have something which is small. So this will be a fast function of z, and this will be a small function of z. Okay. If we look at the graphical interpretation of what we are looking at, this is exactly the plot of this function, okay, with one part which moves very fast and one part which moves very slowly. The fast part here, okay, has if you take the amplitude of the first part, you will have a period which is given by 2 pi divided by delta kz, which is exactly this expression here. So the spacing here between 2 consecutive minima of the function is given by this expression, whereas the distance between the 2 big peaks here is given by this expression here. So this is called, delta z is called the resolution, okay, because it is approximately the width of the main peak of the response of one single scatterer. So if I want to measure another one and be able to measure exactly the amplitude, the other one should be located at where this function equals to 0. Okay, so this is called the resolution, and this is called the ambiguity because this function here is periodical. It repeats itself every z amp. Okay, so if I want to measure an environment, let's say I want to measure a forest, in this case, my forest should not be, the ambiguity height here is of 30 meters. So it means that my forest should be smaller than 30 meters. Because if I measure the ground response here, I will also find it around 40 meters and around 70 meters and around 100 meters in elevation. Okay, it is periodic function. So sampling is very important. So you need to have a small sampling in order to have a large height of ambiguity, or at least the height of ambiguity, which is much larger than the extent of the scene you want to measure in elevation. But you want to have also a nice resolution. Then you need to have a large bandwidth here, given by delta K. So it's a bit contradictory. Anyway, you need to have a large number of images because you need a small spacing and a large extent at the end. Okay. The ratio between the ambiguity and the resolution is given by the number of images. So let's have an illustration. This is the response you get for a target located at 10 meters in elevation, okay, with a given baseline, okay. The baseline and with 6 images. In this case, you have a given resolution, which is of 5 meters here in elevation, and you have an ambiguity of 30 meters. Okay. What happens if you divide the baseline by 2? You say, okay, instead of flying with this distance, I just would like to fly with half the distance. In this case, you will have a loss of resolution since the first minimum here is located at 10 meters from the true position of the target. But of course, you relax the constraints on the ambiguity. The ambiguity went up and you don't see it anymore on this plot, okay? So the ambiguity is much higher. On the opposite, if you keep the same baseline and you measure, instead of measuring 6 images, you measure 12, of course, you will have a much better resolution, okay? Instead of having 5 meters, you will have 2.5 meters in elevation, which is great, okay? And you have an unchanged ambiguity because the spacing between 2 acquisitions is the same. Okay? Ambiguity is dictated by the spacing and resolution by the extent. And of course, you have the last case when you divide the baseline by 2 and you multiply the number of images by 2. In this case, the extent is unchanged. So you have the same resolution, but the ambiguity went off to much higher value. Okay. So how to choose in practice? The rule of thumb that almost everybody follows used to be this one when the flights costed a lot. And today, in fact, they found a way to combine many more flights than what they used in the past. But this is one kind of reasoning that you can apply if you want to design a tomographic experiment. You could do something like this. You select a baseline or configuration. You know, your plane, if you want to use a plane, flies at 3,000 meters. From 3,000 meters and with a given baseline, you can compute the ambiguity. Okay, the ambiguity should be larger than twice the elevation of the forest you want to look at. And if you look at all the data sets that are delivered by ESA in the TomoSAR campaign, in the AfriSAR campaign, this is more or less the rule of thumb they were using. They use 2.5, between 2.5 and 3 times the maximum height. Okay. For tropical forest, the maximum height you may expect, you may know this better than I do, but it's around 40 meters. Okay. And so you should be much higher than this value. But if you are too large, it means that for a given number of images, your resolution will become very coarse. So what you would like that in order to discriminate the ground and the top of the trees, you would like at least to have 3 resolution cells, okay, 3 pixels to describe the forest. This is the minimum, okay, 1 for the ground, 1 for the top, and 1 in the middle, okay. So it means that in this case, you should have at least the resolution should be not larger than this. So if you make the ratio of these 2 constraints, you end up with 6 images. And this is exactly the number you are going to use in the practical, the number that was used in the TomoSAR campaigns, and biomass will use 7 images. But this is more or less the same idea, okay? So now we are happy, we have a stack. We have a stack measure over in Gabon. I think, no, this is not the site. I think this is La Lope, not the test site around the one you will study later. And if we apply the formula, we apply the linear filter, which is a Fourier transform, okay? And we take the square modulus of the results, and you get an estimate of the reflectivity in elevation. And this is great. When you look at it, you see, wow, you can follow the ground, and you can have the response of the treetop. So you are able to measure forest. But when you look at it don't know. Oh, this is a filtering. Okay, when you will look at it on the PDF on the slide, you will see that these estimates are very noisy. Okay, they're extremely noisy. Why? Because SAR data are affected by a kind of noise. It's not a noise, it is an effect. It is a coherent effect, which is called speckle. Speckle is what makes SAR data difficult to use for people who are familiar with optical data and with multispectral data. And this is why there are many more people using multispectral data and optical data than SAR data, because one of the reasons is this one. Okay, it's because you need to filter them and you never know how to do it properly. So you will see for us, we are lucky we don't have to use a very clever techniques. A simple filter is enough. Okay. Okay. 2 words about speckle. Speckle is not a noise, and it is a coherent effect. It comes from the fact, you will see later, that we are summing coherently. When you do imaging, you have an integral somewhere, and you sum responses from scatterers which are located inside your resolution cell, and the result can be constructive or destructive. Okay, when you sum complex numbers, you never know. You never can guess absolutely the amplitude of the results. And this is why over this region, which is in fact extremely homogeneous, if you were working on this region, you would find that there is when you are located on a white spot here and on the black one, you cannot see it on the ground. You are surrounded by grass and you don't know why people will see a black or a white pixel. This is because inside the resolution cell, you will have tens or hundreds of contribution, and one pixel you're lucky, the intensity is high, and on the other one it's low. Okay, so how can we model this? It's easy to represent. Okay, SAR is as I said before, it's a sum inside a resolution cell, C, of the coherent reflectivity of the scene you are looking at, with a term which depends on the distance between the sensor and the objects. Okay, when you are in a situation like this one, or you have a strong scatterer in the middle or inside the resolution cell, let's say you have a calibrator, a metallic reflector, which reflects strong intensity toward the radar. And when you make 2 realizations, when you measure this scatterer and you come back 1 day later and you make another measure, okay, from exactly the same position, you will have a result. The results are almost similar from 1 day to the other. This scatterer is said to be coherent because the phase of its response doesn't change over time. Okay, why? Because it's a metallic place, a metallic reflector, and if you don't move it, it doesn't change its way of reflecting. Okay. On the other hand, when you look at rough surfaces made of grass, okay, or even worse, forest volumes, they change from 1 day to the other, from 1 hour to the other. Why? Because the leaves change. Okay, there's a little bit of wind, the configuration completely change. Even depending on the time of the day at which you make your measurement, there might be water going up in the tree and going back in the roots, and this change completely the correlation properties. Okay, because for us, when you do a radar, you don't see nature the way people do. You see it as a conductor or non-conducting body. Okay, when something is full of water, it's conducting, and when it is not, it is not. It is a dielectric medium. Okay. And this changes during the day. And when you make 2 realizations, like one measurement at 1 date and another one 1 hour or 2 hours later, then you don't have any more the same realization at all. Okay, and the phase change. Okay, and this kind of environments here are said to be affected by this noise. Okay, this sum of contributions which have equal comparable amplitude but completely changing phases, and the results. The arrows in red change a lot from one measurement to the other. So how do we cure this problem? We cure it using a little bit of very simple signal processing. Okay, if you consider the original image, this one, okay, and under the hypothesis of a Gaussianly distributed speckle. I've said it, I will not comment it anymore. If you want, we can talk about it, but it would be out of the scope of this lecture. Then you can show that the variance of the image, I mean, the variance is the variations between black and white on the image, okay, the variance is huge. It is given by the mean, the square mean, which is the maximum, one of the maximum value you can get. Okay, it's maximally random. When you just take several realizations of the scene and you average them, then the variance has been divided by L, the number of independent samples you use. Okay, to make things simple, I just here presented some histograms. Okay, computed from values that I simulated. These are original values, and the means, this distribution or this histogram correspond to mean values that are equal to 0.5, 1, 2, 4, and 8. Okay, when I look at the curves here, it's hard to guess which curve, which plot corresponds to which mean. Okay, why? Because we have an exponential distribution. It is almost impossible to guess. Okay. When I apply this kind of filtering, I just average two values, 8 values, or 32 values, and you see that the distribution starts to concentrate around the mean value. Here it's easy to say that this distribution corresponds to the mean of 8, this one to the mean of 4, 2, 1, and 0.5. It's easy, okay? So it means that I reduce the variance. So the secret here is averaging, okay? How do you average? How do you create this realization? You are not going to ask people to fly 20 times over the same scene to have the independent realization. They will not pay for this. Instead, you can sacrifice a little bit spatial resolution. Okay, this is the full. Sorry, you will see on your slides. There will not be the square effect. Okay. This is the original full resolution image, which is affected by speckle. And we are going to apply a sliding filter, which is called a convolutional filter. Okay. How does it work? It's very simple. In the pixel here in the center of the filter will be equal to the sum of all the pixels divided by the number of the pixels. So you just average the intensity. It's an averaging filter. Okay. And at the end, you get this image here, which is, if you, in your head, if you remove the rows which are not on my screen here, you will get a very homogeneous environment. Okay, the objective here, this is one part of the grassland around GLR in Oberpfaffenhofen in Germany. So it's very homogeneous. It's only grass. And the objective here is to get something, an estimate which should be as constant as possible, because we know this environment has a constant reflectivity. So this kind of filtering works very well, and but it has the tendency to blur isolated targets. Okay, why? Because when you apply, it's like if you had a sponge, you know, and you are applying the sponge on a fresh painting. So you homogenize the painting, but when you have one point, you kind of spread it. Okay, and the result of this spread, it can be not what you were looking for when you want to analyze, for instance, urban environments. Okay. So this is in this case, this image is much better. This is the intensity image, and this is the phase image. Okay, the phase image is really random. Okay, so you see that the distance between the sensor and the scatterers we are looking at is random, in fact, over environments. But there is some information in it, okay? Because from differences of two phase images, we can find the Mount Etna. So it means that there is information, but it is hidden behind the one of the speckle. Okay? So this is the single look image, okay, the original one, and this is after applying the N by N boxcar filter, and during the last 20 years, there have been many different versions of speckle filter proposed in the literature. One of them is the so-called Lee filter, after Yongsen Lee, who attended many of these Polarimetry conferences in the past. And he applied something which used directional filters in order to avoid smoothing isolated targets and smoothing over edges. It's an edge-preserving filter. And to finish this overview of speckle filter, these are examples you can find on the website of a French guy who designed some non-local speckle filters. It's Charles de la Dalle in Bordeaux. You can visit his website. It's very interesting, and he gives examples of filtering results, very advanced ones, okay, which are excellent for a built-up environment and complex scenes. However, for us, as I said before, we will use the boxcar filter. It's enough, okay. We wouldn't know what to do with the high-resolution results. It's hard to, because we don't know the ground truth anyway. No, nobody really went into the jungle to measure what we're trying to analyze. Okay, so if we come back to the speckle filter, why did I make this digression around the speckle filter? For just to explain you that at the end, what you want to do is to average several. Okay, you take the original image you have, you take the square modulus of the image, okay, and you average several realization samples in the surrounding of the pixel. And how do we do this when we perform tomography? We do exactly the same. You have your data, you combine them coherently to estimate the response at a given height. You take the square modulus of this value, estimate it at a given height in the spatial surrounding. Okay, you apply a boxcar filter and you average. The thing is that once you have done this, in fact, you don't know, but you have manipulated the matrix when you have done this. In fact, this manipulation here is exactly the same as this one. Okay, and we like this one. Why? Because it manipulates a matrix operator which contains all the second order information we need to perform SAR tomography. Okay, so we applied here a coherent combination. The result was coherent, complex, amplitude and phase. We took the square modulus, we averaged in the surrounding pixels, and at the end, this is exactly equivalent to doing this, exactly this, to apply a filter to multiply by a vector on the right-hand side, left-hand side of a covariance matrix, the covariance matrix of the data. For those who know the covariance matrix, this expression here is trivial. For the others, I prepared a slide, okay? Because you are going to program it in the computer room, so you better know how to manipulate this. This is the only small technical step you will need to master to do tomography. So how do we compute this? This matrix is written like this. This, for those who I did not explain it, this H means transpose conjugate. Okay, it's Hermitian operator. So if you have a vertical vector, the transpose is this one, and conjugate, you change the phase. You multiply the phase by -1. Okay. And when we do this, computing this matrix, in fact, is we can do this easily by computing each element here, from R11 to RMM, and along the diagonal or off diagonal terms. And their expression is given here. For RII, for one element along the diagonal, I just take the classical formula I was using for 2D images, and in fact, on the diagonal of this matrix, I have intensity estimate. So this is just the 2D reflectivity of the image, okay? And here, I am doing the same operation of the diagonal, but instead of taking the highest element of the input vector, instead of using the highest image, I will use the JS one, okay? So I will do exactly the same operation, but I will take two different images, okay? And by doing this, in fact, I am just preparing the data for a interferometric estimation. Okay, the phase of the off-diagonal elements is exactly the interferometric phase between the first and the second image, between the first and the MES image, or between the second and the MES image. Okay, so these are interferograms, and the amplitude here can be related to of course, to the intensities of the image and to a coefficient here, which is called the coefficient of correlation. You may know this, and in interferometry, this is called the coherence. Don't know why. This is a specific name. And coherence, if you want to deal with interferometry data, is a very important concept. We will manipulate it at the end of this lecture. So the beamformer, which was what we did at the beginning, I said, oh, it's just a Fourier transform. In fact, when you want to apply it to second order statistics, to have filtered results without or with a reduced speckle effect, you just need to compute this formula here. You just take a matrix and you multiply it on the right-hand side by a vertical vector and on the left-hand side by a horizontal one. with conjugate phase. Okay, this expression is exactly equivalent to this one, to a coherent combination, and then you average. Okay, and why do we do it with the matrix? Because when we do with the matrix, we can also apply this estimator, this technique to other kind of estimators, and in particular the Capon one. Capon estimator is another way of estimating the power and of estimating the location of scatterers in the spectral domain. Why is it so different? Fourier relies on Fourier transform, the relationship between phase and position, okay? And Capon is kind of enhanced Fourier transform. The objective of the Capon technique is to minimize the output power at the output of the filter. I want to minimize the output, but I want to maintain a unitary gain at a given elevation. So this is what I have in blue, is the response I have when I apply the beamformer, and in red is what I am looking for when I apply Capon filter. I'm just trying to solve this problem. I would like the result of the analysis to be like the red one. Of course, I will never reach it, but this is the objective, okay? And to do it, in fact, you can make calculations. For those who are interested, we can talk about it later. You can make some derivations, and you find a form of filtering which has this one, which is not so far from the beamformer. You see that instead of having a quantity, you just divide by this quantity, and inside the quantity, instead of manipulating the covariance matrix, you just take the inverse of the covariance matrix. And the result is worthwhile, okay? When you apply it to simulated value, the result is fantastic. You see in practice, it's not that spectacular, but with simulated value, it works very well. This is in blue, the response of the beamformer with a very wide main lobe, okay? Because we have two targets. The targets are two objects, sorry. In radar, we always speak about targets, but I should say scatterer, okay? We have two sources. Two very close sources, and of course, the beamformer, the spacing between the two sources is so small that the beamformer cannot discriminate them. So we have one big lobe saying, okay, there is something below it, but you don't know if you have a single target or two. And when you apply Capon technique, you find that in fact there are two ones. Okay. Except from this ability to reduce the psi lobe, okay, you don't have any more psi lobes. These are these kind of ripples here of the response. You have less psi lobes, and you have an improved resolution. For the rest, Capon is also sensitive to ambiguity, to ambiguous processing. It is very similar, in fact, to the beamformer, but it has an improved resolution. So some of you who studied physics know that when you win on one side, you lose on another one. Okay, so we lose a little bit with Capon, we lose a bit of statistical accuracy. The amplitude you estimate might oscillate, is not as robust as the one of the beamformer, but it's a price to pay to get a better resolution. Okay. Okay. Can go to the next one. The other one was about irregular sampling. Okay. So how does it work in practice? In practice, you can apply. Okay, when you get data, when you download the TomoSense data, you will have the images. Now you know how to compute the covariance matrix. Okay, and you just compute this. You will learn during the practical how to compute the beamformer and Capon estimates. And the true formulas of these estimators use the true covariance matrix, but nobody knows the true covariance matrix because you have data, you have a limited number of pixels of realization to estimate it. And so in practice, you replace the covariance matrix by its estimate using L samples. And sometimes this way of doing has an influence on the stability of the results. Okay, for the beamformer, the influence is very small. You don't see a big difference. For the Capon, you can see a difference. Why? Because you are computing an inverse, and the inverse of a matrix is always something sensitive. Okay, if the matrix is not well estimated, you may have a result with a diverging result. Okay. Means that there is a configuration for which you are dividing by 0, and then the result is extremely high. Okay, you will see. I will give you an example. So how do we do this? If you are in such a situation, how do you do this? There is a small trick. In fact, you take your matrix and you add a small quantity, a matrix which is proportional to the identity matrix multiplied by alpha. Alpha is small, okay? You need to tune it. And if you do it, then the inversion of the matrix is well conditioned and the result is okay. Okay. In practice, very often you have to do this, and this is called diagonal loading. Okay, because you load the diagonal matrix in your matrix, in your covariance matrix. Some examples of beamformer processing and Capon processing in practice. So this is the beamforming result computed over the Parakou test site, the tropical forest in French Guiana. And you see that due to phase terms, because you know that the planes who measure this data were flying, and when you fly in the plane in such regions, the trajectory is never really rectilinear, and of course, people who process the data try to compensate all these errors, but sometimes there are some remaining terms, very small phase screens that may affect the quality of your tomographic focusing. In this case, these phase screens create a replica. See here, I have the top of the forest, and here I have a kind of replica of this top some meters higher. And this is not due, this is just due to phase errors. Okay. And when you apply Capon, you remember Capon, the objective of Capon is to minimize the side lobes. And in practice, in general, it really kills the side lobes that are away from the true response. So it's very good. It can be dangerous sometimes when you have a scene, but it does not happen with forest, but when you have a scene which actually looks like this one. Let's say that you have a strange forest with one stage and another one, then in this case, Capon will have destroyed information. So you better take care when you apply it. Another example of TomoSense. Okay, this is a profile computed, the beamforming profile computed over TomoSense, and you see that the phase compensation was not perfect, and this is what you get when you apply Capon. So everybody can guess where the ground is. The ground is here, and this is the tree elevation. You will see during the practical, it's amazing to see how tomography can actually estimate correctly the tree height. It works very well. Don't know what oh yes, okay. So this is a data set which has been acquired 2007 or 9 by the GLR in Sweden, by the SAR2 at L-band. And here I represented the result of the beamforming estimator for different polarizations. You will see tomorrow what the polarization is with me in the morning. And this is the Capon result. And when you look at this, when you have such a big difference between beamforming and Capon, you should be very careful and say, oh, something is going wrong. Okay, something is going wrong. What happened here? My matrix was badly estimated. The covariance matrix was badly estimated. It was very, very few looks, not enough samples. Okay, so when you invert it, the result shows very high variations. Okay, so in order to modify this, I should maybe increase the size of my speckle filter. Instead of working with a 5x5 box, I should work with a 7x7 or 9x9. Okay, and I could add a small diagonal matrix like this one, so that the results become, the inversion becomes well conditioned. Okay, this is the only cooking recipe you need to know. This diagonal loading and the size of the average filter is the only processing parameters. The rest is okay. Some examples of how tomography works over urban environments. This is now an old image of the city of Dresden, Germany, acquired by a former GLR sensor. And we have only 3 images, you know. 2 images, you do interferometry. 3 images, you start to do tomography, but it's really a tough condition. And in addition, you know, urban environments are very dense, and you may have several contributions falling into the same resolution cell. Here you have a response from the ground, from the top of the building, from the double bounce interaction here between the ground and the wall, and many contributions. And in this case, with only 3 images, this is the result of the beamforming. Okay, this doesn't look like a building. This is the result of a Capone estimator. It doesn't look like a building. And just for you to know, there are other estimators that you can use that have a much better resolution. Okay. Of course, you lose something somewhere. I don't tell you what, but of course, there's always a trade-off. Okay, but there are some high resolution solutions that exist. And of course, in this case, you can get an estimate of the building height and building locations inside the image, which is not as clear as what you get with the LiDAR, of course, okay, but it starts to be interesting to compare them. We took some examples of built-up environments where, of course, tomography worked very well, and this is one of the differences between LiDAR and radar reconstruction. LiDAR is a nadir-looking device, okay, which looks at the things from the top, and the SAR is a side-looking device. And there was a gap between these buildings here and this one, and with the side-looking device, we were not able to actually recreate the gap between the buildings. So just to tell you that even when you have a low number of images, there are some solutions to actually reconstruct the 3D environment you are working on. An application of tomography we did in 2010, so now it's a long time ago, over the tropical forest of Parakou, French Guiana, data acquired by the former French ONERA sensor. No, it was already SETI. The ONERA sensor. ONERA is very close to here. The data at that time, this data set was unique because we had a resolution of 1 meter in range at P-band. P-band, means you mean the center frequency is around 300 megahertz. Okay, and if you want to have a 1 meter resolution, you need to have a bandwidth of 150 megahertz. So it means that the system was fantastic. It's very hard when we consider that a good system has a ratio between the carrier frequency and the bandwidth of 10. And in this case, it had a ratio of only 2. So it's fantastic. It was now many systems can do it. And the vertical resolution was 12.5 meters. And we were at least near range, and you were using 6 images. So now you know the ambiguous height. Huh? You can do the calculation. Okay, we have 6 images. The resolution is 12 meters, so it makes 72 meters of ambiguous height. 72 meters is much larger than the tree height you may expect over this forest, which is around 40 meters. So it was well designed. Okay, so this is the an optical image of this site. This is the polarimetric SAR image. Tomorrow you will know why it is colored. Okay. So this is more classical single pole image with over the LiDAR estimate of the ground and of the top. I say estimate because LiDAR in urban environments, you can believe it, it's very accurate. Over tropical forest, you might have some surprises because very often the LiDAR cannot see the ground because the vegetation is so dense. So you have very few points over which you can be confident. And then the people, they interpolate when you take the LiDAR DTM and you just compute the slopes over below the forest, you would be surprised. They look very linear. They look, depends on the interpolator, which was used by the people who designed the DTM. Okay. But nevertheless, we take this as a reference because we don't have any other ways of doing. And when you apply, you take these data, you download them from the ESA website, and you apply the Capone technique, you get these results over this profile here. You have a distribution of the energy in the vertical direction, which is the following one, and it is very highly related to the LiDAR profiles. It really follows the LiDAR profiles very well. You see, the three top correspond to the black line, and the bottom here corresponds to the end of distribution of the energy in the elevation direction. Of course, there are some polarization for which it works better than the others. And tomorrow you will know why HH is better than VV. If you have to choose one, I wouldn't choose VV. I would choose HH if I had a choice to do. Why? Okay, let's say why all the polarization have a large response for the forest canopy, which is very random. It's like a big volume, but on the ground, double band scattering is a very dominant scattering mechanism, and it is well seen in HH and not so much in VV. Okay, so these are the estimates we were able to compute when you look at, and these are very old results. Today we can do better, but at that time, this was the maximum we could do. And you see that the main difference between the LiDAR and tomographic estimate is a question of resolution, spatial resolution, because when you estimate height with a radar, you need to speckle filter. And when you speckle filter, of course, you blur your results. It's a price to pay. Okay. Some applications, if you want to detect objects below a canopy, okay, these are the evident, obvious military applications, but you can think about it also in terms of geophysics. If you want to see something below snow cover, below ice, or if you want to detect rivers, one of the secondary objectives of biomass is to image prehistorical rivers in dry regions in Africa. Okay, it's about geology. They want to measure the structures that do not appear when you look at optical images. You only see the surface, which looks very homogeneous. But below, we have some colleagues. One of them is Philippe Payou from the University of Bordeaux, who are sure they will find some. They know because they made some experiment. They will find some hidden structures over some in Namibia in very dry regions. Okay, so looking at objects that are hidden below a volume, has also some civilian applications and interesting ones. So in this case, it was a more military-oriented one. There was a truck outside the forest, a truck below the forest, and when you apply spectral analysis techniques, you are able, of course, to detect the truck below the forest, outside of the forest, and below the forest, the result was, okay, you could see something, but it was not exactly obvious if these scattering patterns belong to the truck or belong to the forest canopy, I mean, to the branches, which represent a very complex volume. And in fact, if you apply, if you look for something else, you try to model your response with something else than scatterers, but if you use continuous functions to model the response of the scatterers, and you have a kind of mixing of isolated or like isolated scatterers plus on the top a continuous function representing the forest canopy, then you can separate both contributions and very efficiently discriminate the objects. So it means that what you can do with tomography depends on your imagination and on your applications. So don't be shy, and if you have just try it. Okay, in this case, it was not. When we look at these results, we were very happy because we had a very nice resolution. We could see something, but when you try to extract actually the truck below the canopy, it was not obvious, and we had to propose a new model, and with this new model, of course, we could discriminate the canopy from the rest in very easily. Okay, now let's go back. Let's go to the last topic of my talk, which concerns the analysis of coherence. Okay, Stefano, we were talking about Stefano, and in his SAR course in Milano, he uses 2 times 2 hours to explain this. So we will use, I think, 2 times 10 minutes. So we will, because of course it will be fastidious for you, because we don't want to go into details in signal processing, but we just want to catch some physical meanings. The objective, if I show you the objective, is to explain at the end. I would like you to understand what this is. Okay, this is something you can compute in 2 minutes. You receive data, you compute this kind of representation, and with this I can I can speak 15 minutes describing you the scene, okay, only by looking at these two images, or when you see a tomogram, and these are interferometric phases corresponding to tomogram, and why they follow this distribution with this baseline and not with the other one. And this, to do this, you need to understand a little bit the physics behind the interferometric acquisitions. And this is what we are going to do in 20 minutes. Okay. Okay, so SAR interferometry is based, okay, this is what you've been doing the whole day. You take an acquisition, another one, you make the phase difference. The phase difference depends on is an indication of the height. Okay, so this kind of processing depends on assumes that the response of the environment of the target or the object you are looking at didn't change between the two acquisitions. Okay. This is the condition, the extreme condition. If of course you fly one day, you fly the other day, and the environment changes, of course the phase difference will be very, very random, and you will not be able to extract any information. Okay, so this information, this assumption is that the intensity is similar from one day to the other. Okay, and more importantly, the position of the object between one acquisition and the others is the same. Okay, they didn't move. Okay, and in order to measure this, we compute what we call the coherence, the interferometric coherence. Okay, this is as I said before, if you consider only two acquisitions, you can compute the covariance matrix of these two acquisitions. When you do it on the diagonal of the matrix, you have the intensity in image 1, intensity on image 2, and here we have what we call a cross-correlation coefficient, which depends on both the intensities and gamma. Gamma is called the interferometric coherence. Okay, it is a coefficient whose modulus is smaller than 1. Okay, so it's between 0 and 1. When you have a coherence with a modulus of 1, you know that your two images are perfectly correlated, perfectly. So you can rely, you can say, oh, the phase difference I'm looking at is the actual one. When the phase modulus is equal to 0, something went wrong, and you cannot trust the phase estimate you have in front of you. Okay, it is not possible to do something with the phase estimate. So it's a nice indicator of the quality of the interferometric information. 2 or 3 graphs to show you how this works. These are plots of the probability density functions, let's say the histograms of phase, for different values of coherence modulus. When the coherence modulus is very high, close to 0.95, okay, the interferometric phase is mainly concentrated around this true value, which is phi0 in this case. Okay, so it's distributed very narrowly around the true value. And when the coherence modulus decreases, the distribution becomes homogeneous. And at the end, when the coherence is 0, you don't need to measure the phase. You can generate it randomly. You will have the same information because it is uniformly distributed, okay, independently of the phi0 value. What we can see on this graph here is that how do we, when we have a coherence which is equal to, let's say, 0.6 or 0.8, can we do something to improve the estimation of the phase? Yes, you can do something. You can average. If you average a lot, okay, if you take a lot of sample when you compute the covariance matrix estimate, of course, the standard deviation of the phase decreases here, okay? This is the curve you have when you have one look. So you make the interferogram and you believe it. And this is what happens when you use a boxcar filter, a 4x4 boxcar filter, then you will have 16 samples and you start to have to reduce significantly the standard deviation, okay? 15 years ago, when you were doing a presentation in a conference about interferometry, people were asking, what was the size of your filter? If you say 3x3, they did not listen anymore to your presentation, okay? Because this was, what you were presenting was meaningless. Okay? This was happened to some of my friends, yes. Some examples of how what is the importance of coherence? These are single look. Single look means you take one image, the other image, you multiply one by the complex conjugate of the others, and you read the phase, no averaging. And without averaging, if the coherence is equal to 1, okay, so this is the true DEM, and this is the phase, and the phase is very nice, okay, you see all the variations. And this is what you get when the coherence is equal to 0.2. It's hard to analyze, okay? You have lots of variations that do not actually correspond to variations of the terrain, but they correspond to your noise, okay, between the two acquisitions. Okay, if you have a coherence of 0.7, increasing the number of looks you use to compute the covariance matrix may solve the problem, okay? Here it is single look, 8 looks, 16 looks, okay? This is much more stable, okay? This is acceptable level. What do we lose? We lose when the phase changes very rapidly, you may lose some details because of your filtering. Of course, you destroy a little bit the resolution of your image. You see, when the correlation is really too low, even if you average a lot, then it's hard to recover. You would need, in this case, to use, I don't know, 50 looks. But 50 looks means that you blur your whole image. So you lose a lot of spatial resolution. Okay, so this is how to estimate coherence. And what is coherence? Coherence is a term of correlation. Correlation means a resemblance between the two images, okay? And this term can be decomposed into many terms. We're not going to go through this, but just I will give you one example by main family of the correlation terms. It can be linked to a signal-to-noise ratio problem. When your signal is not high enough compared to the acquisition noise, it can be due to temporal variations. You measure once, 1 day, 2 days after, it has been raining between the 2 days, and the correlation is gone, etc., etc. Okay, so all my explanations have been provided by my friend Andreas Schreiber from the DLR. And this is the image of the DLR, by the way, close to Munich. It's when 20 years ago, we didn't have many SAR images, so we are all playing with the same data sets. So this is the S-band close to the DLR. Yes. Okay, maybe not. This is the motorway and this is the S-band. This is the runway in front of the DLR. These are buildings, forested areas. This is a city. And this is a coherence image taken with between 2 images with a moderate baseline, okay, and the moderate time lag between the acquisitions. And you see that here the correlation is very low and the intensity is very low. This is due to the fact that this is the runway of the airport, and when you measure from the side, most of the energy is scattered into the other direction because at L bands, okay, the runway is very smooth. And what comes back to the radar is a very small amplitude signal, which is comparable with the acquisition noise. So in this case, there is so few information that the correlation is very low. And this is called signal thermal or system decorrelation. Another one is due to the change between 2 acquisitions performed at a different time. So when you wait only for 1 hour between the 2 acquisitions, you have a kind of coherence map. And when you wait for 3 months, this coherence really decreases a lot. Okay, you see that everywhere where you had natural environments like agricultural fields and forested environments, the coherence has gone because the trees have moved, the leaves have moved in the trees, and there is no way the scatterers you are looking at are not at the same position. So everything is different. Okay. So in this case, the resemblance between the 2 images is very low, and you cannot use anymore the phase. Okay, this is why you cannot do in SAR with Sentinel-1, for instance, when it had a 6-day repeat pass orbit at C-band, it's very extreme. Okay, you need to be very lucky if you want to do to get a lot of images and to be in very nice conditions so that the environment didn't change. Over desert, you can, okay, because there is no vegetation if it doesn't change. Okay. of a volcano, and think it's still the same, always Mount Etna in Italy, and acquired by ERS. You saw this morning, ERS was launched in the beginning of the 90s, and they were doing interferometry with ERS-1 and ERS-2, and there was a one-day gap between the two acquisitions. And over this environment, this Mount Etna, there is no vegetation at the top, and then the coherence was high. And this is the same image, but taken between same sites with two ERS-1 acquisition and a temporal lag of 60 days between two acquisitions. In this case, you see the top of the mountain is highly decorrelated. It doesn't happen very often, but it has been snowing between the two dates. And the environment changed, and the images were not correlated anymore. So the black stain you see here is due to snow at the top of the mountain. And the last decorrelation, which is really what is interesting us, is called volume decorrelation. It is due to the fact that we are measuring a volume, and as I will show later, this volume can decorrelate, and the decorrelation depends on the baseline you are using between the two acquisitions. Okay, so how do we model this? In a very simple way. You know that, or if you don't know, no, you don't know it, but I'm telling you, the correlation coefficient in elevation can be computed or can be modeled from the distribution of energy in elevation, okay, from the tomogram mainly, using this kind of integral representation, okay? So this is at the top, this is sorry, at the bottom, you have the intensity of the image, and this is the cross correlation coefficient. And when you make the ratio of these two, you get the coherence. So you have a kind of Fourier transform relationship between intensity of distribution of intensity and this correlation coefficient. So how can we use this in order to analyze volumetric environments? It's easy. We just considered very few scattering mechanisms. Okay, this is, I know some of you here do modeling using radiative transfer. We're not going to do this for two reasons. Radiative transfer is naturally incoherent, and we want to model the phase. And second, it's way too complex. Okay, we just want to analyze something very simple. For us is a response from the bottom, from the ground, a response from the canopy. Okay, and there is no refraction inside the medium because it is a low density medium, and this is reasonable. Okay, we don't see any refraction effect in tomograms. Over snow, we see it. Okay, but over forest, we don't experience it. And we are going to consider a response from the ground and one from the canopy. So let's start with a response from the ground. Okay, and we just start. We don't want to think too much. We just start from the expression of this coherence. It's an integral. When you compute the integral here, the denominator integral of Dirac, okay, for us, the ground has a reflectivity, which if you look at the ground from the side in the elevation direction, it has a reflectivity which is different from zero exactly on the ground, and after nothing, and lower than the ground, nothing. So for us, it's kind of a Dirac distribution, okay, which is localized exactly well at the height of the ground. And if we compute this correlation value, we get something which is just the classical interferometric phase. So when we look at the surface, at the ground, we get a phase. Okay, we didn't learn anything, but at least the model works well. When we look just at the volume, just imagine you have a volume flying in the air without ground below. Okay, something you can try to model into an anechoic chamber in the lab. Okay, at the uni, we did it, but in the nature it does not happen. So you have a kind of volume, and in this case, you can try to see what is the correlation, the coherence pattern of this volume, and you end up, if you consider that the volume has not a noticeable attenuation, it scatters back some energy but does not attenuate too much the wave during the propagation, then the relationship between this distribution of energy and the coherence is a Fourier transform. And you may not know it, that the Fourier transform of a rectangle is a sink. Okay, so we get a sink-shaped coherence, okay, which is like this. So depending, okay, now you start to think on how we are going to analyze the coherence values. based on this kind of model, when you have a coherence, when you have a small trees, if you just had a flying volume in the air, okay, if for a very shallow volume, you will have a very high coherence here. And for a much wider volume, your coherence will become low. So the measure, the fact that the coherence is high or low depends also on the width of the volume you're looking at. Large forests are likely to decorrelate more than small ones, okay? So this is why we use the coherence as a measure of the amount of volume we are looking at the volumetric density, or at least the amount of scattering media within a given volume, okay? And you will see on Wednesday that my colleagues from DLR, they use this to invert the forest height directly. Now, what happens if you have a volume with, of course, an attenuation inside? Okay, it means that the wave, when the wave propagates, okay, it is scattered back to the radar and also in other directions, different from the one you are considering, okay? And of course, there is an attenuation. If you have a constant attenuation, you have an exponential reflectivity profile, and the relationship between tree height and volume height and correlation changes depending on the extension within the medium. If you have a null extension, you go back to the sink profile. If you have a very high extension, then the coherence is very high. Why? Because if you have a high extension, the wave does not penetrate inside the volume, okay? Because it is what contributes back to the radar is just the top of the volume, so a very shallow part. Okay, you see that there is a physical interpretation of what we are looking at. Of course, the phase terms, in the case of a non-attenuating medium, the phase was exactly located in the middle of the volume, exactly. Of course, when you have an attenuation, this value is not, depends on the attenuation, and what we see on this plot here is that the phase term is located between the middle of the volume and the tree top. So when you have an interferogram of a volume, your phase, if you convert your phase to height, you will find something ranging between the middle of the volume and the tree top. And of course, we never see flying volumes. When there is a volume, means there is something below, of course. And then we have the sum of two contributions. We have the contribution of the ground, which is an exponential, and we have a contribution of the overlying volume, which is something like a sink, okay? And when we merge these two information, we get to this expression here, where you have M. M is called the ground to volume intensity ratio. Okay, it is the ratio of the intensity backscattered by the ground and the one backscattered by the volume. If M is equal to 0, means the response of the ground is very low. What you see is only the volume. Then, if you want to analyze forest, this is what you want to guess. You want to isolate this part. Okay. If you're not interested by forest and you want to analyze the ground, then you would like to have M equals to plus infinity. I mean, in this case, the volume intensity will be close to 0, and then you will have only the response of the ground. But this is something you don't set this. You make one measurement and you fall into one configuration, which you cannot choose it. Okay. Are there ways to choose to tune these parameters? There are two ways. Okay, at least, or maybe three. Okay, one would be to change the acquisition frequency. At small wavelengths, you know that you will have a strong attenuation. Yeah, at large wavelength, like biomass, you will see the ground. Okay. Another one would be to change the polarization. This you will see Wednesday, okay, with my colleagues. Of course, you can try to take a polarization for which the response of the ground is large and the one of the volume is small. And another way would be to not only look at one interferometric phase, but look at many ones with different baselines. Why? Because if I go back here, you see the sink is a function of the height of the forest, or the width of the volume, but also on the wave number. And changing the width or changing the wave number has exactly the same effect on the coherence. So if I look at the coherence, the modulus of the coherence for different KZ value, I will be able to guess the true value of the depth. Okay. And this is what is proposed here. You will just say, okay, I will do a tomographic experiment with one baseline, double baseline, 3 times, 4 times, 5 times this baseline. And when I compute this, when I look at the correlation values I get, I can guess the configure, or I can guess the characteristics of the forest I'm looking at. Just one final 2 or 3 slides now, just to explain you what you can do with what we learned today. These are tomograms computed over this Swedish forest at L-band in HH, HV, VV polarization. Don't care about the polarization. We learned this Wednesday. So let's look at one. Here you have no forest, here some forest with the ground, okay? And here we just tried to represent the height, okay, the phase center height for the different baselines. So this is for the first baseline between the first image and the second, first image and the third, first image and fourth, fifth, sixth image. Okay? And we just took the phase. Okay. Of course, we had compensated the ground elevation, so the phases are not wrapped anymore. So there's no more wrapping. We just want to check what's going on with these phases, and you see when the baseline is, of course, the baseline between 1 and 2 is smaller than 1 and 3, and etc. Okay. Here, in this direction, the baselines increase. And when we have a very small baseline, the phase center is very close to the treetop. Okay. Very, very close. The waves, in fact, what you are measuring is close to the treetop. And if you knew the ground, then you could guess the tree height only from this. Okay. But when the baseline increases, you see that you start to see more and more the ground contribution, and the phase center at the end with a larger baseline for exactly the same point your phase center is exactly on the ground. And this is why tomography works. Tomography works because for the same point, when we combine all these interferogram, we can go from the bottom to the treetop. Okay. And this is how imaging works. It's another way of looking at imaging. And why do we have this kind of, when we have a small baseline for a given volume depth, we have a very high correlation value. And when the baseline increases, the volume is not correlated anymore. And what we see is only the ground. And the nice thing is to see that this also is consistent with what happens in the range direction. So this is a near range close to the radar. And this is far range, far from the radar. For a given baseline, a given spacing between 2 acquisitions, the KZ in near range is always much larger than in far range. So the equivalent baseline here is larger in near range than in far range. And you see that here, for this configuration, you start to go on the ground in near range. Here, you're still on the treetop. And when the baseline becomes larger, here you are more on the ground, and then you go up to the treetop, etc., etc. So you see that kind of an effect which slides along the range direction. Okay, same experiment, and now so this is this Swedish site where you have this amplitude image of the forest. So when you look at this, what can we get from only from intensity? We know that here it's likely that there are no trees, and the rest looks very homogeneous. Okay. But when you look at the LiDAR profile, you see that there are forests with different tree heights. And this is an image, okay, of the coherences and phase values computed for the different baseline. So this is the coherence between image 1 and image 2, image 1 and image 3, 1 and 4, etc., etc., etc. Okay, 1 and 5, 1 and 6. And this is the phase difference between 1 and 2, 1 and 3, 1 and 4, 1 and 5. And this is why I was saying that the German pilots are very accurate. You see that in our case, we have almost a Toeplitz matrix. Toeplitz matrix means that what you have, the difference between 1 and 2 is the same as that between 2 and 3, 3 and 4. So it means a very, very regular baseline sampling. Okay. These data really follow the model. It's like in the textbook. Okay, you see almost no difference. The phase pattern between the two, when you follow this diagonal here, the faces looks like it is very, very similar. So what we see here, we see that there are some stains like these white stains that never decorrelate, whatever the baseline, okay? For a small baseline, this is white. For a large baseline, this is white. What does it mean? It means there is no volume, okay? We see just exponential J phi, and this is characteristic of a surface only, okay? Here, in the surroundings, you see that the decorrelation is very strong for large baseline and very small for small baselines. This means that, in fact, these pixels are dominated by the volumetric decorrelation. Okay, for small baselines, you have almost no decorrelation. For large baselines, it's very much decorrelated. So this is typical of volume. This corresponds to forest. And when you combine this analysis with the phase information, then you can understand why the tomograms give this value. Okay, so this is something we do very often. When I want to know what's inside the data set, I just compute the coherence. I just look at what decorrelates, what does not decorrelate. If I see some strange phase values, and after, of course, you can just plot a tomogram to see what you are going to do this afternoon. Okay, we need to break. Okay, thank you very much for your attention.